Welcome to this walkthrough of LeetCode problem number 1674, minimum moves to make array complementary. In this problem, we'll explore how to minimize the number of moves required to make all pairs in an array complementary. Let's dive into the problem and uncover an efficient solution. In this problem, you're given an integer array called nums which has an even length n and an integer limit. The task is to divide the array into n/2 pairs so that each element of the array belongs to one and only one pair. For any pair, A, B, we define its complementary sum as A plus B. The range of possible complementary sums is determined by the smallest and largest values each element can have. Since the minimum value for an element is 1, the smallest complementary sum is 2. Similarly, the maximum value for an element is limit, so the largest complementary sum is 2 * limit. You're allowed to modify the values of the array elements within the range, 1, limit, as many times as needed. The goal is to ensure that all pairs have the same complementary sum, while minimizing the total number of changes required. To understand this better, let's look at an example. Suppose the array nums is 1, 2, 4, 3, and the limit is 4. Initially, we divide the array into two pairs, 1, 3, and 2, 4. The complementary sums of these pairs are 4 and 6, respectively. To make all complementary sums equal, we can modify the second pair, 2, 4, to become 1, 3. Now, both pairs have the same complementary sum of 4. Since only one modification was needed, the minimum number of operations is 1. In another example, let's take nums as 1, 2, 2, 1, and limit as 2. The pairs are 1, 1, and 2, 2, with complementary sums 2 and 4. To make the sums equal, we could change the first pair, 1, 1, 2, 2, 2. After this change, both pairs have a complementary sum of 4. Here, 2 modifications were required, so the minimum number of operations is 2. Now consider nums as 1, 2, 1, 2, and limit as 2. The pairs are 1, 2, and 2, 1, and both already have a complementary sum of 3. Since no modifications are needed to equalize the sums, the minimum number of operations is 0. This example highlights a case where the array already satisfies the conditions, so no changes are required. The problem also comes with constraints and important edge cases. The length of the array n is always even and can go up to 10⁻⁵. Each element in the array falls between 1 and limit, where limit can also be as large as 10⁻⁵. Key edge cases to consider include scenarios where all elements in the array are identical, which requires no changes, or when the limit is very small, narrowing the range of possible complementary sums. Additionally, the solution must handle large input sizes efficiently, ensuring it works within the given constraints. To solve the problem of minimizing moves to make all pairs in an array complementary, we first need to understand the concept of complementary pairs. A pair, represented as nums I and nums n1I, is complementary if their sum equals a specific target value. The goal is to determine the optimal target value that minimizes the total number of moves required to adjust these pairs, where a move is defined as incrementing or decrementing an element within the given limits. One way to approach this is through a brute force method. In this approach, we test all possible target sums, ranging from 2 to 2 times the limit, as this represents the smallest and largest sums achievable by any pair. For each target, we calculate the total moves needed by iterating through all pairs, adding up the adjustments required to make each pair complementary. However, while the brute force method is straightforward to implement, its computational cost is significant, as it involves nested loops that scale with both the array size and the limit. This makes it impractical for larger inputs, where efficiency is critical. To address the inefficiency of the brute force approach, we turn to an optimized method using the sweepline technique. The key idea here is to avoid iterating over every possible target sum and instead focus on efficiently calculating move requirements across all potential targets. For each pair, nums I and nums n1I, there is a specific range of target sums that can be achieved with minimal moves. This range is bounded by the sum of the two elements and their respective limits. Using a differential array, we can represent how the move requirements change at specific points along this range. The process involves updating the differential array for each pair, marking where move adjustments start and stop. By sweeping through this array, we calculate the cumulative moves for each potential target sum in linear time. This eliminates redundant computations and improves efficiency significantly. The sweepline approach reduces the complexity to O(n plus limit, making it feasible for much larger inputs. However, while this method is highly efficient, it does require a strong understanding of the problem and careful implementation of the differential array logic. The strategy we chose to solve this problem is the optimized approach using the sweepline technique. This method stands out for its ability to handle larger input sizes efficiently by leveraging the problem's structure to avoid redundant calculations. Unlike the brute force approach, which is computationally prohibitive, the sweepline technique achieves linear complexity relative to the array size, making it both scalable and practical. This approach works because it focuses only on the points where changes in move counts occur, allowing us to track ranges and calculate results with minimal overhead. Additionally, it aligns well with the constraints of the problem, ensuring both correctness and optimality. While implementing the differential array and sweep logic may pose some challenges for beginners, the performance benefits make it the most effective solution. Alternative methods, such as binary search or dynamic programming, were not pursued as they introduce unnecessary complexity without offering significant advantages for this problem. Overall, this strategy strikes the right balance between efficiency and maintainability, making it ideal for real-world scenarios involving large datasets. In this problem, we're tasked with making all pairs in an array complementary by minimizing the number of moves required. A pair, defined as nums I nums n1I, is complementary if their sum equals a given target value x. To achieve this, we can either adjust the values of the array elements or leave them unchanged if they already satisfy the condition. The challenge lies in minimizing the total adjustments across all pairs. To solve this efficiently, we use a range-based prefix sum approach. First, we need to understand the pairing and the target sum. The array forms pairs from its ends towards the center, such as nums 0, nums n1, nums 1, nums n2, and so on. For each pair, the sum naturally falls within a range determined by the values of the two elements. The goal is to adjust these sums to match the given target x with the minimum number of moves. These moves fall into three categories: no moves if the pair already sums to x, one move if only one element needs adjustment, and two moves if both elements require changes. To efficiently determine the number of moves needed, we employ a frequency array, also known as a difference array or delta array. This array helps us track how adjustments affect the ranges of sums. Instead of iterating repeatedly over all pairs, we update the delta array to reflect the impact of changes. Here's how it works. For a pair, A, B, we calculate the valid ranges for 2 moves, 1 move, and no moves based on the target sum x. For instance, if 2 moves are needed, we increment the delta array at the lower bound of this range by +2. Similarly, ranges where 1 move transitions to no moves are updated with -1, and ranges transitioning back to requiring 1 move get a +1. By iterating through all pairs and updating the delta array accordingly, we capture the cumulative impact of adjustments efficiently. Finally, we aggregate these updates to determine the total number of moves required for each possible target sum, tracking the minimum value across all targets. The key insights behind this algorithm significantly reduce complexity. First, by focusing on ranges of sums rather than iterating over each possible target, we achieve range compression, which allows us to handle the problem more efficiently. Second, the use of a difference array ensures that we can update move ranges in constant time, avoiding expensive nested loops. This optimization is crucial for handling larger arrays. Additionally, the algorithm is designed to address edge cases. For example, in a single element array, no adjustments are needed since there are no pairs. Arrays with repeated values or extreme differences between elements are also handled seamlessly by the range-based approach. The primary data structures we use include the frequency array, or delta array, to track the effect of adjustments, and a prefix sum array to compute cumulative move counts quickly. Together, these structures enable us to solve the problem efficiently while maintaining clarity and accuracy. Analyzing the algorithm's complexity, we see that it operates efficiently within linear time. Processing each pair and updating the delta array takes O(n) time, and aggregating the results to compute cumulative move counts is also O(n). Thus, the overall time complexity is O(n). For space complexity, the delta array requires space proportional to the range of possible sums, which is O, max, nums, plus 1. The algorithm's key operations include computing valid ranges for all pairs, updating the delta array for those ranges, and using cumulative sums to determine the total moves for each target sum. Finally, we return the minimum result. To better understand this, consider an example where the input array is nums equals 1, 2, 4, 3, and the target sum is 5. The pairs are 1, 3, and 2, 4. The sum for the first pair is 4, and for the second pair, it's 6. We update the delta array based on these ranges, calculate the cumulative sums, and find the minimum total moves, which in this case is 1. This example demonstrates how the algorithm efficiently minimizes adjustments while ensuring correctness. The provided solution employs a prefix sum approach to efficiently compute the minimum number of moves required to make all pairs in the array complementary. Here's the detailed explanation. Step 1, Initialization. We begin by initializing a delta array, which will track the net change in the number of moves for each possible sum. The size of this array is 2 *limit plus 2, to accommodate all possible sums and their ranges. Step 2, Iterating through pairs. We iterate through the first half of the array to process each pair, nums, I, nums, n1i. For each pair, we calculate the contributions of their ranges to the delta array. 1. Default case, 2 moves adding 2 moves for all sums initially. 2. 1 move contribution * decrease moves for sums that fall within the range, min, a, b, plus 1, max, a, b, plus limit. 3. 0 move contribution * specifically adjust delta for the exact sum of the pair, marking it as requiring 0 moves. Step 3, Calculating minimum moves. We iterate through all possible sums, from 2 to 2 * limit, accumulating the net changes tracked in the delta array. During this process, we calculate the minimum number of moves required to make all pairs complementary. Efficiency. This approach effectively reduces the problem's complexity to linear time, n plus limit, by leveraging the prefix sum technique. This is a significant improvement over naive approaches that would involve costly nested iterations or recalculations. Edge cases. The solution handles edge cases such as arrays with the smallest possible size, n equals 2. Maximum and minimum values of nums and limit. Large arrays where computational efficiency is critical. Overall, the solution ensures correctness by systematically accounting for all possible ranges of sums and efficiently computes the result using prefix sums. Here, we start by importing the necessary Java libraries, then defining our solution class and the min-moves method. The goal of this method is to calculate the minimum number of moves required to make the array complementary within the given limit. First, we determine the length of the input array nums and define a delta array to track changes in the number of moves for specific values of x. The size of delta is 2 * limit plus 2 to account for all possible value ranges. Next, we iterate through the first half of the array, pairing each element A from the start of the array with its corresponding B from the end. For each pair, we update the delta array to reflect the impact of different types of operations. Specifically, we increment delta 2 by 2, reduce the range starting from math.min, a, b, plus 1, adjust the exact sum a plus b, and handle ranges beyond math.max, a, b, plus limit plus 1. These adjustments ensure that we account for all possible transformations of the array pairs. Finally, we initialize a moves variable to track the cumulative operations and a result variable to store the minimum moves encountered so far. The second part of the implementation begins with a loop that processes all possible values of x, ranging from 2 to 2 * limit. For each x, we update the moves variable by adding the corresponding value from the delta array. We then check if the current number of moves is smaller than our previously recorded minimum, updating the result variable when necessary. Once the loop completes, we return result, which represents the minimum moves required to make the array complementary. In the main method, we provide an example usage of the solution. We initialize an instance of the solution class and define a test case with the input array nums equals 1, 2, 4, 3, and a limit of 4. The program prints the output of the min-moves method, which demonstrates how the algorithm processes the input and calculates the result. This example helps illustrate the functionality of our implementation in a real-world scenario. We start with the first example where nums is 1, 2, 2, 1, and the limit is 2. The first step is to initialize an array called delta with a size of 2 * limit plus 2, which in this case is 6. This array will help us efficiently track changes in the number of moves required for different sums. Initially, all elements in delta are set to 0. Next, we iterate through pairs of elements from both ends of the array. For the first pair, which is 1, 1, we calculate the smallest possible sum as min, 1, 1, plus 1 equals 2, and the largest possible sum as max, 1, 1, plus limit plus 1 equals 4. We then update the delta array accordingly. We add 2 to delta 2 to account for the default move count for this range, and we subtract 1 from delta 2 to adjust for an exact match. Additionally, we subtract 1 from delta 2 and add 1 to delta 3 to handle the contribution of this pair to sums outside the exact match range. After these updates, the delta array becomes 0, 0, 2, minus 1, 1, 0. Now, for the second pair, 2, 2, we repeat a similar process. The smallest possible sum is min, 2, 2, plus 1 equals 3, and the largest possible sum is max, 2, 2, plus limit plus 1 equals 5. We then update the delta array accordingly, and the new state of delta becomes 0, 0, 2, minus 2, 1, 1. To calculate the minimum number of moves required, we use the delta array. We initialize moves to 0 and res to infinity. We then iterate through all possible sums from 2 to 2 * limit plus 1, which is from 2 to 4 in this case. For each sum x, we accumulate the value from delta x into moves and update res as the minimum of its current value in moves. At x equals 2, moves becomes 2, and res is updated to 2. At x equals 3, moves remains 2 after adding delta 3, so res is updated to 0. At x equals 4, moves increases to 3, but res remains 0. Therefore, the minimum number of moves required for this example is 0. In the second example, nums is 1, 2, 1, 2, and the limit is still 2. As before, we start by initializing the delta array with a size of 6, all zeros. For the first pair, 1, 2, we calculate the smallest possible sum as min, 1, 2, plus 1 equals 2, the exact sum of the pair is 1 plus 2 equals 3, and the largest possible sum is max, 1, 2, plus limit plus 1 equals 5. We then update the delta array, resulting in 0, 0, 2, minus 1, 0, 1. For the second pair, which is also 1, 2, we repeat the same calculations and updates. This time, the delta array becomes 0, 0, 4, minus 2, 0, 2. After processing all pairs, the delta array is ready for the next step. To compute the minimum number of moves, we again initialize moves to 0 and res to infinity. We iterate through the sums from x equals 2 to x equals 4. At x equals 2, moves becomes 4 after adding delta 2, and res is updated to 4. At x equals 3, moves decreases to 2 after adding delta 3, so res is updated to 2. At x equals 4, moves remains 2 after adding delta 4, and res stays at 2. As a result, the minimum number of moves required for this example is 2. Moving on to the third example, nums is 1, 1, 1, 1, and limit remains 2. We first initialize the delta array to 0, 0, 0, 0, 0, 0. Then, for each pair, 1, 1, which is repeated twice, we calculate the updates to the delta array. After processing both pairs, the delta array becomes 0, 0, 4, minus 2, 0, 2. Finally, we calculate the minimum number of moves for the third example using the delta array. Starting with moves equals 0 and res equals infinity, we iterate over the sums from x equals 2 to x equals 4. At x equals 2, moves increases to 4 after adding delta 2, and res is updated to 4. At x equals 3, moves decreases to 2 after adding delta 3, so res is updated to 2. At x equals 4, moves remains 2 after adding delta 4, and res stays at 2. However, since all elements in the array are already equal, the actual minimum number of moves required is 0. Thus, the final result for this example is 0 moves. To determine the time complexity of this algorithm, we break it into three main steps. First, the initialization of the delta array. The array has a size of 2 asterisk limit plus 2, and initializing it requires a single pass through its elements. This step takes 2 asterisk limit plus 2 operations, which simplifies to limit. Next, we process the pairs of elements in the array nums. Since the array has n elements, there are n//2 pairs. For each pair, A, B, the algorithm performs a constant number of updates, specifically 5 modifications to the delta array. This means the total time for this step is proportional to n. Finally, we compute the prefix sum and determine the minimum moves. This involves iterating through all possible sums, which range from 2 to 2 asterisk limit. The number of iterations is therefore 2 asterisk limit 1, and since each iteration involves a single addition, this step also simplifies to limit. These three steps together form the foundation of the time complexity analysis. When we combine the time complexities of the three steps, we get the overall time complexity of the algorithm. Initializing the delta array takes limit, processing the pairs in nums takes n, and calculating the prefix sum and minimum moves takes another limit. Adding these together, the total time complexity becomes n plus limit. Now let's examine the space complexity. The primary space usage comes from the delta array, which has a size of 2 asterisk limit plus 2. This is proportional to limit. Additionally, the algorithm uses a few auxiliary variables like moves, res, and loop indices, each of which requires constant space, or 1. Importantly, the input array nums is not modified, and no additional space is used to store intermediate results related to nums. Therefore, the total space complexity is dominated by the delta array, resulting in limit overall. To appreciate the efficiency of this algorithm, let's compare it to a brute force approach. A naive solution would iterate over all possible pairs in nums and compute the cost for each possible sum x from 2 to 2 asterisk limit. For each sum, this would require looping through all pairs in nums to calculate the number of moves. With n//2 pairs and 2 asterisk limit, 1 possible sums, the time complexity of the brute force approach becomes n asterisk limit. In contrast, the algorithm we've analyzed avoids this inefficiency by using a difference array to pre-compute costs for all sums in n plus limit time. This optimization significantly reduces the dependency on the number of possible sums. Furthermore, whether we analyze the best, average, or worst-case scenarios, the algorithm's performance is consistent. It always processes all pairs in nums and iterates through all possible sums, making the time complexity n plus limit in all cases. The mathematical proof of the algorithm's complexity hinges on the role of the delta array. By transforming the problem into one of prefix sum computation, the algorithm achieves linear time performance relative to the size of delta, which is 2 asterisk limit plus 1. Additionally, the loop over the pairs in nums operates independently of the prefix sum computation and takes linear time in terms of the input size, or n. Since these two components, processing pairs and calculating the prefix sum, are independent, their complexities are additive. This gives us the overall time complexity of n plus limit. By efficiently combining these steps, the algorithm is able to achieve optimal performance under the given problem constraints, making it significantly faster than the brute force approach while maintaining clarity and scalability. One common mistake is misunderstanding the range of possible sums. Many assume the target sum must be within the bounds of the array's minimum and maximum values, but in reality, the range spans from 2, which is the sum of the smallest pair, to 2 times the maximum element in the array. Overlooking this can lead to incorrect calculations or missed edge cases. Another frequent pitfall is relying on a brute force approach, where you iterate through all possible target sums for every pair. This quickly results in a time complexity of n squared, or worse, which is computationally expensive for larger arrays. Additionally, boundary conditions in prefix sum calculations are often ignored. If you don't handle cases where indices exceed valid bounds, you might run into runtime errors or produce incorrect results. Lastly, when dealing with overlapping ranges of valid sums, it's easy to mismanage these overlaps. This can result in double counting adjustments or underestimating the moves needed, both of which can derail your solution. Odd-length arrays introduce another layer of complexity. When the array has an unpaired middle element, it's a special case that's often overlooked. Ignoring this can lead to edge cases being missed during calculations. From an interview perspective, it's important to showcase an optimization mindset. Start by explaining the brute force approach to demonstrate your understanding, then transition to discussing optimizations, such as using an auxiliary array to track the frequency of adjustments for target sums. Efficient solutions often leverage data structures like prefix sums or difference arrays, so be prepared to explain how these tools reduce the time complexity to O(n). Pattern recognition is another key aspect. This problem is a variant of range frequency problems, so highlight your ability to identify overlapping ranges and minimize redundant calculations. Lastly, emphasize your testing strategy for edge cases. These include arrays with uniform elements, extreme values, or even minimal sizes, all of which can reveal hidden flaws in your approach. This problem shares similarities with other challenges on LeetCode. For instance, problem number 1090, largest values from labels, involves optimization under constraints, much like adjusting the array to minimize moves. Problem number 1658, minimum operations to reduce x to 0, uses sliding window techniques to minimize operations, a strategy that can be adapted here. In problem number 253, meeting rooms 2, overlapping range analysis is critical, just as it is when managing valid sum ranges. Finally, problem number 2007, find original array from doubled array, also involves frequency maps and meticulous counting. When exploring alternative approaches, brute force is the most straightforward. You try every possible target sum and calculate the moves for all pairs, but with a complexity of O(n)², it's impractical for larger inputs. A more efficient option is prefix sum optimization. By using a difference array to track the range of adjustments needed for each target sum, you can bring the complexity down to O(n). However, this method requires careful implementation to avoid common pitfalls like off-by-one errors. An alternative approach to consider is binary search, though it's less common. In this method, for each pair, you use binary search to determine the minimum adjustments required for a given target range. The complexity is O(n) log n, making it slightly less efficient than the prefix sum optimization, but it's often easier to reason about. This trade-off can be worthwhile, especially in scenarios where simplicity of implementation is prioritized over raw performance. While binary search may not always be the optimal solution, it's a valuable technique to have in your toolkit, particularly for problems involving sorted arrays or specific range queries. By combining these strategies and adapting them to the problem constraints, you can develop a robust and efficient solution that handles both the typical cases and the tricky edge cases effectively. To wrap up, we explored how to solve LeetCode problem number 1674 by leveraging prefix sums and range updates. This approach demonstrates the importance of efficient computations in array-based problems. Thank you for watching, and don't forget to like and subscribe for more insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!